In this video, we'll discuss right triangles, and we're doing that because there's a lot of unique properties to right triangles that can be helpful. One of those is the Pythagorean theorem, which states that a triangle is right if and only if the leg squared plus the leg squared equals the hypotenuse squared. And this is true for only for right triangles. And the converse is true. If we know that the leg squared plus leg squared equals the hypotenuse squared, then we know the triangle must be right. Now you may ask yourself, well, what's the hypotenuse? The hypotenuse is always across from the right angle, so it's always the longest side. That's important. Now, what if a triangle isn't a right triangle? We can use what's called the Pythagorean inequality to help us out. And what is that? Let's talk through it. So first, if we want to try to determine is it right, acute, or obtuse, we first start with what is the longest side of that triangle, because that has to be the longest side, and at most, if it is a right triangle, then it has to be the hypotenuse. The second thing we want to do is verify that the three measures do create a triangle. So that means that if I take the two shorter sides, which we'll call the legs, that sum has to be more than the longest side. Now, if those two things are true, now I can use the Pythagorean inequality, which says to take the two legs, square them and add them, and compare that to the longest side squared. And what we know if it's equal, it's a right triangle. But if that sum on the left side is greater than the longest side, it's acute. And if the longest side squared is greater, then it's obtuse. So while instead of having the equals, which is the right, we can use this inequality to help us determine acute versus obtuse triangles. So say we have three measures here, where we know that we have AB, BC, and AC, which are 7, 4, and 10 units respectively. And we know that we want to know, is it a triangle? And if so, what kind of triangle is it based on right, acute, and obtuse? So first thing, the longest side is 10 units. We can see that 10 is the greatest of them. Now let's make sure that the three will make a triangle. So 7 plus 4 has to be greater than 10 for this to make a triangle. 7 plus 4 is 11. So yes, that's a triangle. Now let's use the inequality. So we're going to square our two values on the left side, add them together, and compare that to the right side squared. So 7 squared plus 4 squared is going to give us 49 plus 16. We add those together, that's 65. Well, 65 is less than 100. Therefore, this is an obtuse triangle, and this is what it would look like if we were to actually construct it with these measurements. Now, within right triangles, we also have some special right triangles. One of those is the isosceles right triangle, or the 45-45-90 triangle. What we know in this case is that because we have two legs being congruent, the hypotenuse will always equal the leg length times the square root of 2. Now you may ask yourself, well, why is that true? So let's think about this from an abstract standpoint. Let's label each leg as L, and we'll label the hypotenuse as H. And we know they are both L because they're the same measurement. So if we think about the Pythagorean theorem, leg squared plus leg squared equals hypotenuse squared. And they are the same measurement, so there are 2 times leg squared. Now, if I want to then know the length of the hypotenuse, I take the square root of both sides. The square root of 2 is the square root of 2. The square root of L squared is L. So the hypotenuse is equal to the length of a leg times the square root of 2. So let's look at an example here. Say I have this triangle that we see is marked as right, and we see it's isosceles. We want to know what's the measure of x and y. Well, this side here is marked as congruent, so it has to be 6. And then to figure out y, you could use Pythagorean theorem, or you can make the recognition that the hypotenuse equals the leg times the square root of 2. So in this case, that would be that the y equals 6 times the square root of 2, doing direct substitution. Here's another example. Now in this case, we're given the hypotenuse and not the legs. So we have to go in the reverse order and use that idea that x has to equal y, and then we also know that the hypotenuse will equal the leg squared, or we can use Pythagorean theorem, where x squared plus x squared equals 64. So 2x squared equals 64. x squared is 32. Take the square root of 32, which is 4 the square root of 2. Again, the other thing you could have said is hypotenuse 8 equals x times the square root of 2 and solved that. You'd end up in the same situation. So if x is 4 square root of 2, we know that y is also 4 square root of 2. The other special right triangle is the 30, 60, 90 right triangle. And where we're going to do our relationship is we're always relating compared to our 30-degree angle in its opposite side. Opposite the 30-degree angle is our starting measure. We'll call that A. And what we know is in relationship to A, the side opposite 60 is that measure times the square root of 3, and opposite 90, in other words, the hypotenuse, is always double that relating angle from the 30 degrees. This relationship will always occur. And you may ask yourself, well, why is that? That's a weird combination. So let's look at here we have an equilateral, a regular triangle MPL. If we draw in the bisector, the perpendicular bisector through P, we're going to label that PD. Remember, what does that do? It makes that 60 degrees become two 30-degree angles, and it makes ML become two congruent segments, MD and DL, because it's been bisected. Now we see right here, we have a 30, 60, 90 triangle. So we're going to use that. So we don't have any given measurements, so we can call segment MD, this segment here, as A. By segment addition postulate and by the relationships we have, we know that DL has to also be L, or has to be A, which means that entire length from M to L is 2A, which means all three sides of our equilateral triangle are 2A. There's our doubling, right? A compared to 2A. Then you may ask, well, how do we get this side? Well, we're just going to use Pythagorean theorem to determine PD. And so we know that that would be MD squared plus PD squared equals PM squared. And we can substitute in the values we have. We have A squared and 2A squared. 2A squared, that means 2A times 2A, which is 4A squared. And I'm going to subtract 1A squared to the other side, leaving me with PD squared equals 3A squared. I take the square root of both sides, and you can't take the square root of 3, but I can take the square root of A squared, so that is A times the square root of 3. So now I have that relationship. A is across from the 30 degrees, A the square root of 3 is across from 60, and then 2A is across from the 90. So let's look at two examples here. In this case, I have the hypotenuse. And what I recognize is that the hypotenuse is always double the side opposite the 30 degrees, and that's x. So the hypotenuse has to be double x, or 2x. So if I divide both sides by 2, I determine that my x value has to be 6 units. Now my y values are crossing the 60 degrees, so I can now use that for help with my relationship, because I know that the side opposite 60 is always x times the square root of 3 in this case, which we just found was 6, so y has to be 6 the square root of 3. Now we can look at one other example here. Say in this case we have the side opposite the 60 degrees. Now again, let's figure out this relating angle from across from the 30 to start with, because everything in the 30, 60, 90 relates back to it. So we know that the side opposite 30 is going to be times the square root of 3 to create the side opposite 60. So 8 the square root of 3 equals y the square root of 3. If I divide both sides by the square root of 3, I'm left with y being 8. Now I can figure out my hypotenuse because I know my hypotenuse is always double the side opposite 30 degrees, which is y. 2 times 8 will give me 16 units.